Excuse me. That's right. Hello, students. Happy Wednesday. Welcome to the stream. We have an exciting day ahead of us. How was assignment 2? For anybody who's just hanging out. Is it pretty straightforward? I know a lot of you guys managed to figure it out, especially those of you who came and talked to me. That's good. Happy to hear that. Yeah, I mean, hopefully it was just mostly copy-paste. I know a few of us struggled to put together the idea of, what objects were where and how do we call functions. But for the most part, I think you guys got it. We'll be introducing this new assignment today. We won't do it yet because we still got a few minutes left. But hopefully in this assignment, you'll also get some more practice with objects. So it's something to look forward to. At least I think. I know you guys probably aren't, but... I made this assignment a few days ago, and I'm super proud of it. I think it's exciting. I think it's a fun assignment. I think you guys will have fun with it. So I'm excited to show it off. Gotta make sure I got everything set up here. That looks good. Okay. What are we going to start with today? Probably notes. Probably just pointers. Yeah. Not that. This is just going to be address. Nice and big. Include IOStream. And I guess I'll cover that as well when class starts. We'll just talk about header guards briefly. Got like 8 people in the chat room. We're gonna wait just 1 second here. Okay. Put that phone away. We don't need it. All right. It's 11:30, so we're going to get started here. hopefully more people come into the chat, and I hope assignment 2 didn't scare a lot of people away. So we'll get started with that. I mean, I guess this will be on YouTube anyway, so people can just go watch it there. So the first thing to talk about today is, well, for one, if you didn't finish assignment 2, the late deadline is tonight. I would recommend turning it in. I usually give most points, even if it is late. So please do that. And I'll message you with helpful tips and stuff. I always do that. The second thing we need to talk about is we're going to introduce assignment 3 and just go over it real quick right now. And this assignment is based off of inheritance, which is what we spent on the last 2 days in class. So I'm going to go ahead and just show you in the assignments tab here. It's a little tiny, but we do have assignment 3 here ready for you guys to download. This one is ready to go. So I know the last 2 assignments I kind of uploaded some versions that weren't good and then they were good. This one is ready to go. So all you have to do is come in here and download this stuff and you can get started. I made this one and I was inspired by, I think, Red Rose last class when he said, all I have to do to make a game is use a while loop. And so I kind of wanted to do that. And so here's what we got going on. We're making a randomized battle game in the terminal. Now, most of the code is done for you. You really only have to focus on the class part and the inheritance part. And I will be going over the code here very shortly. But let's just kind of briefly talk about some stuff in here. So we're going to be coding up some player classes, just like I did last class. There's some code on Web Campus for that. Though it's not exactly the same, it gives you kind of an idea. And in this game, we're going to pit between 2 and 5 teams. So you're allowed to pick. And they're going to do a big battle, okay? And it's completely randomized. And I did all the randomization parts for you, so you don't have to worry about that. Teams are comprised of players from 3 character types. Now, I kind of mix and match my words here. I'll call these player types as well. So hopefully you don't get confused when I do that. But it's also like a class, right? The Ranger class, the Warrior class, the Mage. So we have 3 character types: Ranger, Warrior, and Mage. And each team will have the exact same amount of players and the exact same amount of character types. So, for example, here I say teams can have a minimum of 1 per each character type, which means the team will have 3 total players. I'm going to switch here to this nice big screen so I can really, get a big zoom in there. Yeah, it looks better, doesn't it? So 3 total players, or maximum 99 per character type, which means each team will have 297 total players. And the program is going to randomly pick and choose players from teams and have them fight, and the team at the end that still has players left will win. Now, as specified in last class, we're not killing anybody in this game. We're family friendly here. They're just battling it out until they have 0 health left, and then they're going to go respawn or take a nap, and they'll be fine. So here are our 3 classes. I kind of just made this little Microsoft Paint diagram. We've got the Rangers, we've got the Warriors, and we've got the Mage. And we've got a triangle that's going on here. So we'll be doing some coding in regards to this. Yep, Pokemon. I love doing it, and I think it's kind of fun for coding, Yeah, so, yeah, I'm taking that from coding, but no worries here. And each class has like a special ability, kind of. So the Ranger can dodge. The Mage can critical strike. And then the Warrior, we just say, has big damage. Okay, so not really a special ability, but rather can just deal more damage. And so if you kind of follow this in a clockwise direction, the Warrior can deal double damage to the Ranger to the Mage, and the Mage to the Warrior. And if you go the other direction, it's halved. So half damage mage to ranger, half damage ranger to warrior, etc. So here's where it gets scary, right? Just kidding, it's not. There are 7 total files in this program. Luckily, you only have to put code inside 2 of the files. And so here's the ones I highlighted for you. You're only going to be dealing with these 2 player codes. And I'll pull those up and show them to you. I coded main, I coded the team, and I coded the game. You are so welcome to kind of look in these if you want. There's nothing in here that you don't know, except for maybe one thing. And I kind of mentioned that, I think. Here, I say, you should know everything you see except for maybe vector.erase, and you can look that up if you'd like. So you should be able to kind of understand what's going on here, especially because I left comments everywhere, but really you only have to look in these 2 files. Now, this is new, right? You've never seen this here before. We've got a game.cpp, a team.cpp, a player.cpp, and main.cpp. What does that mean? Well, we're introducing a new compiling style. And so just like when we separate function prototypes above from the definitions below main, right? Or when we're in classes, we kind of put the prototypes up top and all the definitions below. We're doing the exact same thing here, except all of the prototypes are within the H files. So there's actually no like major coding in the H files. And the CPP files contain all of the function definitions. Now this is handy because, I guess we'll put it here in some notes. We're going to call this implementation files, in which the .cpp is separate from the .h. Is someone can specify the general shape of the class or the design, right? Without actually coding the definitions. And in this way, we can compile different implementations of the class functions each time we compile. Okay? So just to kind of restate that, we can compile different implementations, meaning that even though the class is going to remain the same in the H file, we can always just recompile the function definitions if we want to change anything. So I'll show you how we code that, or compile that. It's really not that hard. And one more thing here, this code will not compile as is, okay? So the last 2 assignments were kind of nice to you on that, where it would compile right away, and you might be able to error your way to victory. In this case, it will not work. So you have to read what I tell you to do. And look what I say. You need at least to do number one, fill in the class prototypes. And 2, put empty function constructor definitions first, just like we did in the first assignments. Otherwise, if you try to compile this, it's going to be like, hey, what is a mage? Where is this constructor? Things like that. Like I said, you really don't have to look in those classes. And I describe only the player stuff in detail, and at the very end of the document, I include the other classes in case. So here's a big player class, UML, right? We've seen these before. We got the variables here in blue. We got the constructors here in gray, and we've got all the functions here that are kind of in this yellow, maybe tan color. And what are you responsible for? All you have to do is the constructors. That's it. And you have to initialize these static variables. And so look how I tell you this. Your code here, player count, a static integer. You need to initialize this in player.cpp. I tell you exactly where to put it. Initialize this static variable. You need to initialize it in player.cpp. Tell you exactly where you need to put it. The rest, I just kind of describe them for you, but you don't have to do anything with them. And then here I tell you exactly what you need to do with the constructors, okay? And I also tell them to put them in player.cpp. So I'm telling you where that these should go. So those are the only things that you have to do for the player class. All these functions here are implemented for you. And then the Ranger class, your code here. The Warrior class, your code here. And the Mage class, your code here. Now, there's a lot of text here, but guess what? I really just copy-pasted this 3 times and replaced, like, some things in here, right? So it's pretty simple, right? I'm just going to tell you to use the inline method, initialize some of the values, or pass values to the constructor. And then I also ask you to print a message, and that's really it. And there's plenty of comments in the code for you to look at. So then you do the parameter constructor, and then you're going to override the deal damage. The reason that this function is an override is because if you're a ranger, you're going to have to check the other player to see if they're a warrior or if they're a mage. And if so, then you're going to modify the damage that's being dealt. You'll also print out a fun little message that says it's either super effective or it's not very effective, just like Pokemon. Now, the Ranger class and the Warrior class are pretty much the same, except you'll just have to change up some values. And then the Mage class is almost exactly the same, except there's an additional function here for critical strike. I already coded this one for you, but basically what the crit does is it's a Boolean function, and it has a 1 in 3 chance to return true. So when you're coding your do damage here, and I even put it in here, I say call the crit function, and if it returns true, print a message, and then the mage can deal twice as much damage. And then the max that a mage can do is its base damage, which is 2, times the super effectiveness, which is also 2, times 2, which is a critical strike. So at most, a mage can deal 8 damage. So there's just a lot of details here for you. It's not scary, I promise. And then here's how we compile it. You have to do 6 constructors and 3 functions for all of those classes. We're going to put all the CPP files together, just side by side. And that's how we compile this function. And then we just, not this function, this code. And then we'll run ./a.out. So that's it. And now I'm not going to go over these. You can read this if you want, but this is the team class and this is the game class. So I know I kind of breezed through that. Please let me know if you have any questions. Of course, you're supposed to read this. And I promise it's not like a night sit-down reading material. I'm just making sure you have all the details. So now we're going to look inside the code real quick, and then we're going to run the code, and then we're going to move on to our material today. So here is, excuse me, player.h. The first thing I'll talk about is just these header guards. Now, what a header guard is it's just going to help us. I didn't tell you when it's due, and I haven't created it yet, but it'll be a week. So probably Tuesday, Wednesday, just like the last assignment was. Next Tuesday will be the regular date. Next Wednesday will be the late time. And this one will be smaller than the other class, or the other assignment. There's still some stuff to do, but... So a header guard is very simple. And you don't always need them, but they're nice to have. And so what this says is, if not defined, and then some name. So it's like an if statement. So it says, if IOStream H, if this name is not defined, then define the name. And then in here is whatever code that you want to include. So some code. In this case, it's just some include IOStream. And then this is something you've never really seen before. But this is just the end of if statement. So when you're going through these codes, you'll see that I do this thing. And it's because I use IOStream in all of these files. In tons of them, in fact. So even if I pull in game.h and I pull in team.h, you'll see that I'm including vector here. In game.h, I guess I don't include vector, but I might want to. And so the compiler will give you errors if you've included vector twice. Notice it kind of looks like the compiler or VS Code is telling me that this is already defined, because in team.h I brought it in, and then in game.h I brought in team, and then I redefined vector. So these are header guards, and what they do is they make sure that I don't try to bring in anything twice. If I happen to bring in something twice, by accident, the compiler will yell at me, and it will be like, I've got 2 definitions for vector. Which one do you want me to use? So do the header guards make sense? You don't have to do anything with them in this assignment. Just know that these are checking to make sure that there's no duplicate headers. Okay? So that's all those are. I don't have to save those. And then now we're finally going to look at the code here. So here's this player identifier class. This is just a player ID. Okay, so if you think about it here, we've got some example player IDs. Each player will have this ID, and it's randomly generated by the program. So this first letter is the color of the team. So we're going to have the red team, the blue team, or the green team, or the yellow team, or the purple team. Those are the other 2. And then this next letter represents their class. So here we have the ranger, we have the mage, and we have the warrior. And then this number is the static ID count. So as more players come in, we'll just increment some integer. And so they'll get this identification number. So this class is just designed to hold that, right? Here's the ID, here's the character type, and here's the character team. They're being initialized to this n value just because there's no character type and there's no team to start out with. There's a default constructor which should never be called by you. You have no use for this. But notice here we've got a constructor here which will take in an ID, a character type, and a team. And then we have this nice function called getPlayerName, which will just return the character's name in this nice format, such as GW22. So this class is here for you just because it's used in the player class. So here it is, the player identifier. So just know what that is. But there's nothing new here that we don't know, right? So here's the static integers. Here's the integer members. Here's the character members. Here's the weapon, the string member. Here are the 2 constructors that you have to code. And then here's all these functions, which I explain in the PDF. And then this is for the ranger. Now you can see here we got this big your code here, right? As always. And look what I tell you to do. You gotta make the ranger class prototype. You gotta make the mage class prototype, and you gotta make the warrior class prototype. Is that hard? No, it's not. Because guess what? The UML is right here. I'd pretty much give it all to you, okay? So you gotta do some public stuff in here. You gotta make 2 constructors. And this is just the prototype, right? No definitions in this file. Though, I mean, you could if you wanted to, but please don't. I tell you if they're static or not. I tell you if they're constant or not. I tell you what their type is, and I tell you what parameters they take. Okay, so just, implement this in the player.h. And recall that this class is inheriting publicly from player. If you don't remember how to do that, check the notes. So warrior class, mage class, and ranger class. So that's all you have to do in player.h. And then at the end it says end your code, and that's it. So let me know if there's any questions with that. Once again, just implement the prototypes for these classes. Now player.cpp is the meat and bones. So Here you can see we got this big code here thing, and I'm just telling you what to do. Why would damage be const? Let me see. Are you talking about deal damage? If you're referring to that, it's because the player that's dealing damage, actually the object won't change at all. The player that's taking damage will be changing. But since the player that's dealing damage is not being altered in any way, that's why this function would be constant. But if you come up here and look in this class, you'll see that take damage is not constant. Because when a player takes damage, then they're altering, the object is being altered. So I hope that makes sense. And that's why it's constant. But the actual base damage is not constant. Yeah. It's a good question. So look, I tell you initialize your statics, and then look, I tell you to do the default player constructor, I tell you exactly what to do. And I tell you to do the parameter player constructor, I tell you what to do. And then that's end your code, okay? So those are the 2 player constructors and the 2 static variables. That's it. And then look, here's all the player functions, right? So you can even kind of reference these if you need help, right? So these are all the other functions for player. You don't even have to do them. And then you see this your code here thing again. And here's what I tell you in the Ranger class. You have to do the 2 constructors in the deal damage override. In the Mage class, I gave you this critical function here. Notice that it's red, and that's because you haven't done the prototype yet. But you still have to do the constructor, the other constructor, and the deal damage override. And then the warrior class, constructor, and then the deal damage override. And that's it. End your code. So I'm going to get to compiling this code. Really, after you figure out one of them, if you manage to figure out Ranger, the other ones are kind of copy-paste. The Mage will be a little bit different, but it's really pretty straightforward. So we're going to run this code. And so look how it's compiled. So we're going to type out our regular main or G++ statement. And then we got to type out all of the CPP files. So the player.cpp, the team.cpp, and the game.cpp. Once we do that, if everything works, it'll compile. And then you just type ./a.out. And here it says, I'm just going to zoom in here a little bit. It says, about to start the battle. How many players per team? So we'll start small. Let's just say that there's 1 per each class, right? So I'll say 1. And how many teams? We'll say 2. Now it's going to fire off real quick. So we're going to scroll back up here. So notice after I enter 2 teams, it says, hey, I create the red team. And it spawns in a red warrior, a red mage, and a red ranger, right? Because there's 1 of each character type. Then it creates the green team. And it prints the warrior, the mage, and the ranger. And then it says team's ready to go. And then all it does is it randomly will pick players to fight each other. Notice that the ranger attacks the warrior. It was not very effective. Notice that this mage attacked a warrior. It managed to deal a critical strike. Look, it dealt 8 damage. And then I'm going to look for one more thing. Notice here that a warrior attacks a ranger, and the ranger managed to dodge it. Now, you don't have to worry about the dodge statement. I did that for you. But that's it. And so it will just print these out. Blah, 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 blah. And then at the end, it will tell us that the red team won and it has 2 players left. Now we can have a lot of fun with this. I don't know why I recompiled it, but when we run it again, we can go, how many players per team? 99. How many teams? 5. And now this is a huge text thing, okay? Look, there's over 1,000 players in here, and the game just randomly ran until the red team won with 5, or the purple team won with 5 players left. If I run it again, I do 99, I do 5, It's going to run again, and it looks like Team Red won this time, has 8 players left. So I wouldn't gamble on this or anything, but it is completely randomized. So ask questions if you need. I'll just show you on Web Campus that here's your coding files. I'll have to edit the PDF, I just realized, because I want you to turn in both the player files. So I'll make a small update to the PDF. And then I have sample outputs here. So here we got sample with 2 teams and 1 player type each, and then a sample with 5 teams and 99 player types each. Okay, so that was 20 minutes talking about that assignment. I hope that you guys are okay with it and excited, and let me know if you have questions. And I'm here to help you. So that'll be due. I'll create the assignment today. It'll be due next the 16th, next Tuesday, late deadline on the 17th. CBay, I'll look into that for you. I was thinking about that myself, and I will show it to you. I'll tell you where we can put it if you want to do that. I'm not going to do it right now because we do have some stuff to go over, but I will look into that, and we will put it in the game.cpp file in the while loop. We can probably wait a few CPU cycles and just kind of let it print out slower. And so we could just copy paste that in there. So I'll let you know, because that would be cool. But I'm letting you know that if you do this 99 teams, it's going to run for like maybe an hour or something, depending on how long you wait. But you can just find it all in here. You can find every example. Not that you would, but you can have fun. Okay. I see I had too much fun with that. I got to put it away. All right, so now we're finally going to move on to our actual stuff. We talked about the header guards. We talked about these separations. Let me go ahead and do this. G++-std is equal to C++11. And then file1.cpp, file2.cpp, file3.cpp, etc. So you understand what's going on there. I'm going to save that. All right, so today we're talking about pointers and pointer arithmetic. Now, maybe you guys have heard horror stories about pointers. I think we'll be okay. But if you have, they are truly the bane of some people's existence. And they're not very intuitive, in my opinion. But they are for people who do systems coding. So C guys and C++ guys generally do operating system stuff. And you need pointers for that. So today, this is week 4. Week 4 and week 5 is a pointer. We got like 2 weeks going on here. Now, I'll have to double check, but I think next Monday is a holiday. And so, instead of having, and we already lost one Monday at the beginning of class. So instead of having 4 days for this, we have like 2 days for this. Now, I can do it, but I may provide a supplemental video when it comes to the memory allocation, but we'll see where we get. I won't put anything in stone yet, and we'll just get going and see how we do. If we go look at our textbook, it's in there. I know most of you probably just going to reference my notes anyway, which is totally fine. But for those of you who like to read the books, we'll let that load and I'll show you where it is. And there's a few things to talk about first. So the first thing we need to discuss is the address, which is it's a hexadecimal. Can anyone tell me what hexadecimal means specifically? You can take a guess. Depending on some of the classes you've taken, such as CPE 100 maybe, you should know. Yep. Let's see. T. Peter asks, are we learning all data structures or just the ones in the chart? Which chart? Oh, are you talking about on my syllabus? Whoops. Where am I going? This doesn't want to load today, huh? Are you talking? Yeah, we're in this class. We're gonna learn linked list, stacks, queues. Yeah, and that's about it. You'll take CS 302, which is a data structures class. So this class really is not a data structures class, but we will learn these things, as well as we'll learn a dynamic linked or a dynamic list, dynamic array. So that could be considered one as well. This is not going to load, so I'm sorry. You can find it there if you'd like. Just look in the table of contents. And so I see red rows and macros got it. Yeah, it's base 16. And so all addresses in C++ are represented by a hexadecimal number, which is a base 16 number. It's just like base 2, right? You know, so I'm even just going to copy paste this because we don't necessarily need to see all of them. But in hex, we've got 0 through 9, just as always. But then we need 6 more numbers. So when we get to 10, that's an A, 11 is a B, 12 is a C, 13 is a D, 14 is an E, and 15 is an F. And so then when we're ready to go up, 16 is represented as 1, 0. And then 17 is 1, 1. And then, you know, dot, dot, dot. And then we get to 1A. So it's really not too bad. So, but that's what we're going to see when we use addresses in C++. That's what we're going to see. So, all variables, objects, variables and objects, kind of the same thing, have an address, and we can go find it. So let's go ahead and do that in some C++ code. And I'm just going to leave this at the bottom. So I ask ourselves, can we see the address? Yes. And so we call this the address of operator. I think. Yeah. Address of. And we've kind of seen this before. It's the and sign. And it kind of makes sense because when we do something like that, usually we're passing something by reference, right? Which means we're passing the address of this object instead of making a copy of it. So they're used differently, but we're going to see how that works. So we're going to keep things super simple today, going back to ints and stuff. Int x is equal to 0. And we can see out x, of course. But where is x? We can say see out the location of x is at. Now we use the address of operator, which is this and sign here. And we put it before the variable. So here we go. How to use it. We're going to say see out this and then some variable, right? Makes sense. So let's see what we get here. Can anyone take a wild guess? Do you think if I run this code multiple times, the address of x will be the same every time? Because it might be, it might not. I would say every time we compile it, it will probably change. Yeah, so I would go on the side of what you two guys have said. It's not going to be the same usually. Because what the compiler does is it compiles your code. And at the beginning, before the runtime, it does all the memory allocation. In the memory, allocation or memory is controlled by the operating system. So what C++ does is it goes to the operating system and it says, hey, can I have some of this memory? And the operating system will say yes or no. I'm going to need you to load in here, please. And so then the operating system will give it the memory, and usually it's going to be a different address. So we're going to run this code ./a.out. And here we got this big scary hex address, right? Yeah, it should change. So this 0x just means that it's an address. It's a hexadecimal address. 0x is not part of the address. The actual address is this number here. 7FFDF5C9211C. It's a nice big number. So let's run it again. Notice that the address changed. Notice that they're kind of close. But what happens was when this program ran, at the very end, when it returned 0, and the compiler automatically generated code to deallocate this memory at the end, this address was then returned to memory. And then when we ran it again, my code went back to the operating system and said, hey, I need an address for this X variable. And it says, here, this one's free. It gives you a new one. So we'll just run it again and again and again, and you'll see that this address is changing every time. So all the time, we don't have access to what address we get. Okay, that's important. So if we wanted to put something like that in notes, operating system controls memory programs must request memory, and in this case cannot always control which address it gets. Okay, so those are addresses. And now we're going to talk about, well, let me check my notes. Now we're going to talk about the dereferencing operator. Dereferencing means that we're going to take an address and we're going to dereference whatever is located at that location. So I'll kind of compile these all at the end, but we're going to do the dereferencing operator. Probably spelled that wrong. Let's see what this does. I think it's okay. That's a lot of E's, you know. E. And so what this looks like is it's the star. Now that's confusing because this is like the multiplication sign, right? But in fact, this is unary. Does anyone know what unary means? Multiplication when binary. Multiplication when binary. And then dereference unary. And what we can do is this. As long as whatever's inside here is an address. Yeah, one operand is correct. So yeah, you're kind of seeing that, right? We got the by in the un there. So the unary means that this operator only takes one argument, and binary means that this operator takes two arguments, right? So in general multiplication, 3 times 2, you need the 3 and you need the 2 in order to use it like that. But when it comes to dereferencing things, we only need 1. So what we can do here is, this is going to be a little confusing, but we're just kind of building ourselves up. Variable located at address. And I'll just kind of bring it down since we're getting a little wide here. So if X is an address, we can dereference it. Now, I know that's a little bit backwards, right? But we're just kind of showing you how these things work. And in a weird way, we could just go on forever. And so this shouldn't be confusing at all. But if we have an X, we can literally do the address of and the dereference over and over and over and over and over again. So we're kind of flip-flopping. So let me know if there's any questions on what this does. We're just going to run the code to make sure that whatever was at that address comes back, right? And so whatever was at that address, it was 0. So here we should say variable located at address will be 0. So variable located at address is 0. And notice that we see out at a 0 here at the end, which, you know, I can dereference this a million times. As long as I take the address right after, it won't matter. So those are kind of two main things that we focus on with pointers and stuff like that. Now we're going to kind of get into the fun stuff. And there's a few things that we should talk about. So the first thing that I want to do is discuss arrays in general. So we'll just leave this as is. We'll save this as a new file here. address2.cpp. Control A, Control C, Control V. We're going to get rid of this. Loaf is coming to say hello, but unfortunately I'm teaching right now, so you can say hi, and then you gotta go. So let's pretend that we have an address. So in this case, we're gonna say int x, and it's gonna be an array of, say, 5 elements, and that's gonna be equal to, say, 0, 1, or, you know, I messed that up already, but there we've got an array of 5 elements. Now, if I see out the address of this, the address of X, we're going to get some address, right? But now let's kind of talk about this. Here's what I'll say. This address, this array, is contiguous in memory, which means that these are all going to be side by side. And so, in fact, if we see out the address of element 1, X located at, and remember how arrays work, right? Some of you struggled with this with your for loops. This is at the 0th index, this is at the 1, this is at the 2, this is at the 3, and this is at the 4. Even though the size of this array is 5, we can only index it at 4. So we can kind of do this thing here. Element 2, element 3, element 4. I definitely didn't want to do that. And element 5. And so it's one less. And let's kind of see what we got going on here. And so contiguous means that they're side by side. I didn't want to do that one. And so let's kind of look at what's going on here. This is the address of the actual array. Notice that the address, notice here that this, let's see, we got a good question here. How many bytes does each memory location have the ability to store? So that is dependent on the type, and we're going to talk about that very shortly. That's a very awesome question. Notice here that Yes, yeah, exactly. Four bytes is an int. You can kind of see the addition going on here, right? So the actual address of the array is here, and the first element is located at that address. Now, I'm not sure if the compiler is going to allow this. I really hope it does. But it might say, hey, this doesn't make sense. And if it does say that, then it's fine. But this is how arrays are handled in C++. And we've used arrays before. This is not how vectors are handled, but this is how arrays are handled. Arrays are stored as addresses. Oh, it looks like it was okay with it. Yeah, look at that. Look at that. So look, I didn't even have to do this and of operator. X itself is an address. And it's the first, these are the same. The first element is the same. And then we add 4 each time. And that's where they're located. So before we go any further on that, how can we tell what the size of each element is? Well, that operator, it's called the size of operator, and it doesn't even look like an operator. But how big is each type? Well, it's very easy. We're going to use the size of operator, and it looks exactly like this. It looks like a function. But in C++, this is considered an operator, okay? So this is an operator. And inside of this, we can either put a size of type, or we can put a size of some variable in this case. So if we wanted to put x in here, we could do that. And what does it do? It returns the size in bytes of the variable. So if we come in here, and I'll put here in some comments, right? Array is an address, right? We learned that. That's how addresses work. So we can see out the size of an int. And then I'm also going to declare, say, maybe a string y. And we can actually see out the size of that actual variable. So that's going to be y. And then I can even do one more thing. Let's make a struct up top. Say this is a student struct. And within our student struct, we've got a string for the first name, a string for the last name. We've got a float for their GPA. And then we've got anything else I care about? Let's say no. Okay. So we've got a struct student. We can even see out the size of a student. This is the size of a string. And then we're going to do this again. Size of student struct. Okay. So I know my face is probably in the way here a little bit, but we're just going to see how big these things are. And then we can tell almost exactly how, how big an array will be based off of the size of each element. So if we compile this again, and we run our code here, we see that the size of an int is 4, which makes sense, right? Because we're adding 4 here every time. 8 plus 4 is C. C plus 4 is, it flows into the next position, right? Just like when you do decimal addition. Size of a string is 8 bytes. The size of the student is 24 bytes. Now let's see if we can figure out why that is. Whoops. So it looks like let's see what the size of a float is. Now I'm assuming that the size of the float is also 8 bytes. If it's not, then I'm going to be upset. and something went terribly wrong with my calculations. Yeah, something did go terribly wrong with my calculations. So size of the float is actually 4. The size of a decimal or a double is actually 8. Now the size of the student appears to be 24. And I wanted to say that that's 8 plus 8 plus 4. But it looks like it takes some bytes to store the name of the structure. But we'll come back to that at a later date. So we have the size of operator. And now we're going to talk about pointer arithmetic and how arrays work. So in fact, we use these brackets all the time. When we want to get inside of an array, we use brackets. Now those brackets are actually an operator. So we don't need this string student anymore. We don't need this stuff. But we do need this stuff. So I'll just show you, right, inside a for loop, if we ever wanted to see out int I is equal to 0, I is less than 5, I plus plus, if we ever wanted to see out each element, we could see out I, and then a little colon there, and then print x located at I, right? And we use these brackets. Those brackets are an operator. In fact, they're the dereferencing operator. And I'll show you that I can recreate this code by doing some pointer addition. Pointer arithmetic is what we call it. Arithmetic. Now we're computer scientists, and I will take the moment to say that you're not always allowed to play with addresses and other code, such as Java, Python, things like this. In C++, we do teach pointers here at UNLV. And so even though knowing pointers might not be the most important thing to a computer scientist, we are learning some good stuff here. And we will be better computer scientists because of it. So if you recall, this is where the first element is, right? So if we take the address of x and we add 4 bytes to it, and then dereference it at that location, we will be able to pull out some value. Now, I do need to put this in some notes. Addresses have a type. And so just like any other variable, we have ints, strings, float, double, I wanted to say decimal there, etc. And this type tells the compiler how many bytes to look at. Does that make sense? So if it's an int address, it's only going to pull 4 bytes out of there. If it's a double address, it's going to pull 8 bytes from that starting location in memory. If we were to cast it, which we will have some fun with next time, we can make some really weird values because we're having the compiler dereference an address that's not actually, meant to be stored in that many amount of bytes or whatever I'm trying to say. But we'll get to that when we do. And so if we add an int to an address, say int x to an address, it will add x bytes or x number of size to an address of type t. It will add x number of size of t bytes. C. If we declare an int variable as a const, it would be less than 4 bytes if it were, say, the number 1, since it wouldn't need to take up the entire container. So I believe a const integer would still be 4 bytes. We'll see, because you can only fit so many numbers within an integer. So if we look up this max size of int in C++, we can kind of pull it over here. We see this big number here. So this is the maximum value that can fit inside an int, and one of those bits is reserved to be signed or not signed. So it can either go in the negative direction or the positive direction. Notice that the negative direction is 1 greater. And then if things are unsigned, that means that the first bit is not reserved for the negative or the positive. And so if it's unsigned, then we can fit, say, double this amount in those data types. So since an integer, a constant integer is the same type as an integer, it would still have the same amount of bytes to store this range of values. But the compiler will enforce that location cannot be changed. In fact, here, if I type short, I think the compiler recognizes that. And if you even wanted to, if you said unsigned short, I guess these are good to learn, though we really probably haven't spent much time on that. So an unsigned int is it's a non-negative 4-byte integer, right? Does it make sense? Yeah. And then an int is a negative or positive 4-byte integer. And then if we were to talk about shorts, I think they're only 2 bytes. But we'll leave that for a later date. So here we've got this, and I'm just going to add values to it. So when I say if we add an int x to an address of type t, it will add an x number of size of t bytes. So if for example, if we have I guess we'll do some code here. If we have a string y, size of string is 8. And then if we take the address of y plus 1, this is the address of y plus 8 bytes. Now I'll do one more example, and please tell me if this doesn't make sense. So if we do an integer x, size of int is 4. If we take this, and this is an address of an integer type, that this is going to add it's going to be the address of x. I guess I need to put the operator here, right? It's going to be the address. No, because I said address of. It's going to be the address of x plus, in this case, 4 bytes. Now, if this said 3, how many bytes will this be? If I said plus 3, how many bytes will we add to this address? $12 bytes. That is correct. Though I do appreciate it is confusing, right? So I know that this is kind of confusing. If I could put this in maybe a formula, it's going to be, I mean, this really is our formula, right? It says if we add an int to an address of type t, it will add x times size of t bytes, right? So that's kind of our formula. X times the size of t bytes. So in this case, we'll take the size of int is 4, and this integer here is 3, so it's going to be 3 times 4. It's going to be 12 bytes. Do another example. One more. If we take a what's small? I guess. So short is 2 bytes. So if we take short, z. So size of that is 2 bytes. Size of short equals 2. And if we take the address of z plus, and in this case, say like 12, we're going to get the address of z plus 24 bytes, right? 2 times 12. Yeah, exactly. Nailed it. Nice job. Okay. So we're going to do this now in this array here. So notice here, and this is what this operator does. Okay. So we'll talk about it. So why we need 4 days to cover this stuff. So I can take the address of x, which I will do just because we've been doing that. And then we're going to add I to it, right? And then there's one more thing we have to do. Can anyone tell me what I have to do? Because this is going to give me an address, right? And if I want it to be the value, located at that address, I'm going to call some operator that we learned. Did the stream just die? Looks like I'm still alive, maybe. Looks like we had a bit of a hiccup there in the stream. So we'll just kind of wait here a little bit. It looks like we're going to catch back up. Hit refresh. Yeah, pause for a second. We should be good now. So now that we're all back, if I want to dereference this, I have to use the dereferencing operator, right? So I'll just come to the notes. If I want to dereference an address, I find here, dereferencing operator. Like I said, I'll clean up these notes, and we're going to call it on this thing here, right? So we're going to dereference the address here. And this is identical to this thing. It is identical to that thing. It's exactly the same thing. So let's check it out. Bobby's going to contemplate life for a little bit. And we'll compile our code. And /a.out. And something went terribly wrong. Something went terribly wrong. So, right, that worked. Let's see what I did wrong here. Let's see what I did wrong here. Definitely got to figure it out, but that should work just fine. Did I assign X to be anything else? I don't think I did. So, it looks like we're getting the right addresses, but there may be some precedence operation here in which the addition is over that, so I'm not exactly sure. Let's just try to compile this code one more time. And then I'll check my notes, because that definitely was not what I wanted to happen. But we can always use a pointer instead, which we haven't even talked to about yet. Let me try it this way then. Why would you do this to me? Maybe I'm saving the wrong file. Okay, there we go. So that's a little bit upsetting. I don't know why it did that, but as you can see, we get the exact same output. I said X was an address, right? So we know that X's address of array. And so I guess if I'm calling the address, oh. We're going off on a small tangent here. If I take the address of an address, it probably returns the address. And so I may have to dereference it twice. So let's see how that works. And if so, then we figured it out. There's one thing that I did want to do. I wanted to print out a little line. Let Bobby contemplate the life here. Okay. Okay. Something very bad happened there. So, I'll get back to you on that. I'm not sure what... I guess if we're returning the address of X, I'll have to get back to you on that one. But does this make sense? If we know that X is the address of an array, if we add some amount of bytes to it, and then we dereference it, we're going to get this exact same thing back. So we're going to kind of put this in the notes. If we return the address of an address, we might get some different address. And then it's just, you see how pointers are the bane of people's existence? Even I am getting kind of confused here. So don't worry, I'm a pointer master. I swear. Maybe not an expert. So I guess master's above expert. So I'm good at pointers. How about that? So we're going to talk here about the dereferencing 2.0. Right, which takes, it's this bracket here. Okay, and what it does is it's the same as xi, right? It's going to be the address of x. But x is already an address, so we'll just say x plus I bytes. Here, let's fix this. Type xi. This is the actual operator. Type xi takes x, which is an address. I'm going to really kind of split this up because I want it to look nice. Plus I bytes, and then we dereference it. Yeah, so I'm kind of going all over the place. I is an int, adds this stuff up here, right? So we know that. So that's what this does, okay? Brackets are just a dereferencing operator, okay? So I know that we've used those before. Now we know what they're doing. They're doing this. They take the address, they add I bytes to it, and then they dereference it. So let's see if there's anything else that I just want to look at. Because we actually didn't get to the pointers today, which is fine. Because we were really talking about addresses, and that's the main focus. So I guess I'll just take 5 minutes to talk about a pointer. But then we're going to get out of here, okay? And I'll clean up these notes. I'll upload our example code. And then I'm going to look into this address of addressing thing that was fooling me because, you know, I'm a little embarrassed, but that's okay. So we'll begin the pointer section. So, a pointer is an address. Macros asks, does assignment 3 use pointers? No, it does not. Assignment 3 only focuses on inheritance code. So if you come here and look in files and go to class code, this is 135 review, classes, inheritance. So these two files here is all assignment 3 uses. The next assignment, assignment 4, will be going over pointers and stuff. So not yet, we got to learn about them first. So a pointer is an address. It's a variable for an address. Pointer is a variable used to hold an address. Pointers have types, just like addresses have types. And how are they declared? We've got some type, some here, and then we put a star, which is like the dereferencing operator. That's already confusing enough. And then we've got a variable name. So in main, if we were going to make a pointer for an int, we do that. And people in general, it doesn't matter where you put this. I like to put it here, because what does this say? This says that this is a pointer to an int. This is a pointer to an int. And so, just to kind of capitalize or on the idea that we had earlier today, let's say we have an int x, the same array that we've been using. Let's actually just copy this code, and I'll show you what the pointer does. It's just pretty much the exact same thing. If we wanted to store the address somewhere, we can take this x array that we've been using, we can then say that the pointer is equal to, now I do want to use the address of operator, and I think that I can fix this if I do this. But I think additionally, if I just said pointer equals x, everything else would be just the same. But let's just say that this is the address of beginning of the array. And this makes sense, right? Because this is for one int, right? And we're going to give it the address of one int. And so now, if we take this pointer, we can even print out the pointer. This will be the last thing we do, compiling this code. If we print out this pointer, we should see the address of the first element of this array, which is the starting address for this entire array. We will see that as we add I to the pointer is of type int, right? It's an int pointer. So it will add 4 bytes every time. And we will see this address or these elements get printed. And I kind of want to mix it up here to make it look obvious. Now I know today was kind of, dinky examples in main. As we learn more about addresses and pointers, we're going to bring out classes and stuff and actually show you what's going on. But before we do any of that, we just need to know what these things are doing. What's going on here with the pointers. So that's the address, right? So a pointer just holds an address. Like I said here, we stored the address of the first element in the pointer. And then we take this address, we add I to it, and then we can dereference it. Aaron asks, and we'll save it for next time, but he asks, does the pointer have to match the data type of the variable you're trying to get the address of? I would say probably the compiler will, I'm going to say no. If you just want to hang out for 1 second even, we'll give it a shot. And even if the compiler does enforce it, there's ways around it. So let's say I have a string G is equal to beans or something. There's always ways around it in C++. Now we have this pointer x up here already. So if I say something like pointer is equal to the address of G, here's what it says. It says value of string pointer cannot be assigned to entity of type int pointer. So it says, hey, this is not what I want. But now here I'm going to confuse you. So don't store this in your brain if it's going to confuse you yet. But we can cast this to type int pointer. So I don't know if you've ever done casting before. But what this says is it takes this address and make it I can make this an int. Or I can make it, well, the cast won't work this way. But if I can make this an int pointer, I can cast it. And then I can try to see out the dereferencing of whatever that is. So how do we dereference an address, right? By using that dereference operator. We're going to get some ridiculous garbage value. Someone says wait here. I'm waiting. I'll drink my tea. And for everyone else, it is 12:46. You're welcome to go if you'd like. We're just going to talk about this goofiness right here. So here's what I'll say about that, Red Rosenrot. You could make an array of addresses. You could make an array of addresses, and each address will point to a different type of something. Yeah, you could do that. But at the same time, why not just make a struct instead? So G, beans. So whatever, I don't know how beans is represented in binary, but it's something like this, right? Where beans is like 1, 2, 3, 4. So that's like the B. And then this is the E, and then blah, 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 blah. That's the E, and then blah, blah, blah. That's the N and the S. So the first 4 bytes of this string, 2, 3, 4, whatever this value is going to be dereferenced as an integer. And so it's going to dereference this as an integer, and whatever that value is, we have no clue what it is. We have no clue, but we're going to just run this code, and you'll see that we can, by casting an address to a different type of pointer, to a different type of address, we can store it in an integer pointer. But you'll notice that the compiler doesn't like it. See, we get some garbage value here. It doesn't make sense. Whatever this is the integer conversion of the first 8 or the first 4 bytes of the string beans, right? Does that make sense? I'll say it one more time. The integer conversion of the first 4 bytes of the string beans. That's what this is. Because it just took that string in memory, it grabbed the 4 bytes, and it dereferenced it as an integer. So we're going to spend a lot more time on these pointers. So don't get scared yet. There's no assignment yet. I'm here for you always to talk about pointers and stuff. And plenty of times will I run into a goofy error like I had earlier today with the address of kind of thing. So just bear with me. We'll get through this together. Thank you for coming to class today. I'm going to take my 10-minute break. Office hours are in 10 minutes. I always appreciate you guys participating in the chat, and I will see you next time.